All right, I'm going to give you a little bit of instruction before we do the last page in this quarter, and you can decide whether you want to do this. It'll be on Canvas as well. The Chapter 4 review, pages 97 to 99. It can either be first quarter or second quarter, depending on whether you think you need a few points extra now or whether you want to just finish up this quarter and have it start second quarter. But I'm going to give you the instruction you need. We talked about isotopes, and we did the lab with the candy, and you found the average weighted mass of those, which would be like the mass number of the isotopes, atoms of the same element with a different mass number, so that means different number of neutrons. Today we're going to talk about ions. Ions are the same element, but this time they have an electrical charge, and they get an electrical charge by changing the electrons. You could change the protons, but if you change the protons, then you have a different atom. So the only way to keep it the same element is by changing the number of electrons, and you can either gain or lose. If you gain electrons, you're gaining a negative charge, so the whole atom becomes negative, and that's called an anion. If you lose an electron, it becomes positive, because at that point you have more protons than you have electrons, so you have a positive atom, and that's called a cation. And my high school chemistry teacher showed me that right in the middle of cation is a plus sign, so that's how you remember which one is the positive one. If that one's positive, the other one has to be negative. And in class, when we tried this and the battery ran out, so I have to redo it. It was chosen astatine. Astatine is number 85 right here on the periodic table at the bottom of column 17. And the electron dot diagram shows 2 s electrons and 5 in the p's. You see the same thing here. Now we're only going to talk about the valence electrons, the ones that have the highest principal energy level, which would be 6. So we aren't going to worry about those. Those are in there. They're important. But as far as finding what's going to happen to the ion, what's it going to do, we only look at what are called the representative electrons, the valence electrons, that are the S and the P. So it has 2 and 5, so it has 7, and one's 8. It's more visual when we look at the orbital notation. Again, the F and the D are behind, so we just look at the S and the P, and we can see that it does want one more electron. The electron dot diagram shows that, put it over here, it wants that extra electron there to give it the stable octet that would make it just like radon. They all want to be like one of the noble gases. If it does that, we add one more electron, it becomes negative. And how many? We added one negative charge, so it becomes a -1. Now you can also look at that. It has a 85 protons, so we have 85 protons minus how many electrons? Well, it had 85 if it was neutral, but we added one more, so minus 86. And that leaves us with a -1, and that's the charge. We write it as 1 minus, put it at, we say, -1. A little bit simpler, if we do, a little easier with that, aluminum, which is atomic number 13, mass number of 26.98. We're going to do the protons, neutrons, electrons. There would be 13 protons, and this would go to the nearest whole number, which would be 27, and this is protons plus neutrons, This is protons, so if I take this, subtract this, I'm going to get the number of neutrons. That's going to go here, so I get 14. And then the electrons, the normal number of electrons, if it's neutral, would be 13 again. So my positives and negatives would cancel. But that's not a happy atom. It wants to either be, here's aluminum right here, and it wants to either be argon or neon. It doesn't care, but those are the two closest noble gases. So if we draw the electron dot diagram, we have the 2s, and then it's the first one in the p, so we have one there. Now it can either fill this up, which would mean that it's going to gain 5 more, or it could lose all that it has, which would be 3. And it's always going to pick the easiest one. It's going to lose the 3. So if it loses those, now we have 3 less electrons. So over here we actually only have 10. To find the charge, it is 13 protons minus, now we only have 10 electrons. Gives us a 3, which is a positive, so when we write the positive, it's a 3 plus. That's the ion. Now, they are put in the chart in a way that makes sense, even if it makes it harder to find them because they're not alphabetical. There is a reason that they are put the way that they are. Let's see if I can. There we go. Okay, all of the first column has a valence of 1. They have 1 electron. They just have 1 s in their outer ring shell principal energy level. This one has 2, and we skip the canyon. They have charges, but they can often have 2, 3, 4, or more charges, and they play by a little bit different rules, and we will learn their rules and how to figure those out, but not right now. These are, I have 3, 4, 5, 6, 7, 8. So these are going to lose 1, so this whole column, its natural ion is a +1. These are +2, skip the canyon, +3. These are the naturally happy atoms. They have exactly 1. They're not going to do anything, so they're 0. They're not going to gain, they're not going to lose. These are going to gain 1 more, so they're -1, -2, -3. They meet in the middle at either plus or -4, which it won't really do either. They'll share. They'll make covalent bonds. But that's 2 chapters from now. So again, the natural valence is +1, +2, +3. 0, -1, -2, -3, and then plus or -4. Now, if we were going to go back over here to the board, hopefully you can see it. If we were going to do this, do it the next way, and you were given, whoops, aluminum 3 plus, how many protons, neutrons, and electrons there are? If we were going the other direction, we would just look on the chart. Aluminum has an atomic number of 13, so it always has 13 protons. And since there isn't a number up here to show that it's a different isotope, we take it as the most common, which since it says 26.98, we just round that off to 27. And again, 27 minus the 13 will give me 14 neutrons. But to get the electrons, I need to have a charge of +3, which means I'm going to have more protons than electrons. The easy way to do this is take the number of protons and do the opposite of the charge. It says a +3, so I'm going to subtract 3. 13 minus 3 is 10. As easy as that. So that hopefully that helps. That's your little lesson on ions, and you will find the same place you found this. You will find the sheet to work on And that's pages 97 through 99, the review questions in your textbook. Enjoy.